Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. 53 years have passed since Eugene Cernan's boots last touched the lunar surface during Apollo 17 in 1972. His final words on the moon, promising humanity's return, hung in the vacuum of space for over half a century. Today, that promise is finally becoming reality through NASA's Artemis program, the most ambitious lunar exploration initiative since the space race. Named after the Greek goddess of the hunt and twin sister of Apollo, Artemis represents more than symbolic continuity. This program embodies a fundamental shift in how humanity approaches space exploration. Where Apollo was a sprint driven by Cold War competition, Artemis is designed as a marathon, a sustainable long-term commitment to establishing permanent human presence beyond Earth. The Artemis program consists of multiple interconnected missions, each building upon the previous to create an escalating ladder of capability. Artemis 1, launched in November 2022, successfully demonstrated the Orion spacecraft's ability to travel to lunar orbit and return safely. This uncrewed test flight validated critical systems that will carry astronauts on future missions. Artemis 2, scheduled for September 2025, will mark humanity's return to deep space with a crew of 4 astronauts flying around the moon but not landing. This mission serves as the crucial human-rated test of all systems before attempting surface operations. The crew will travel further from Earth than any human has ventured since Apollo 17. The crown jewel, Artemis 3, aims to land the first woman and the first person of color on the lunar surface by 2026. But unlike Apollo's brief surface stays lasting mere days, Artemis missions are planned for week-long surface operations, with crews exploring the lunar South Pole, a region never before visited by humans. This geographical choice represents strategic brilliance. The South Pole contains permanently shadowed regions that harbor water ice deposits, potentially billions of tons frozen in ancient craters. Water isn't just essential for human survival. It can be split into hydrogen and oxygen, creating rocket fuel. This transforms the moon from a destination into a stepping stone. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. The technological foundation of Artemis rests on 3 primary components: the Space Launch System, or SLS, rocket, the Orion Crew Capsule, and the Human Landing System, or HLS. The SLS stands as the most powerful rocket NASA has ever built, capable of sending 27 tons to the moon, nearly 4 times Apollo's capacity. Orion represents a quantum leap from Apollo's command module. This spacecraft can sustain 4 crew members for 21 days in deep space, features advanced life support systems, and includes radiation shielding crucial for long-duration missions beyond Earth's protective magnetosphere. Perhaps most revolutionary is the HLS, built by SpaceX using their Starship vehicle. Unlike Apollo's single-use lunar module, Starship is designed for reusability and massive cargo capacity. It can deliver over 100 tons of equipment to the lunar surface, enabling construction of permanent infrastructure. The implications extend far beyond national prestige. Artemis represents humanity's first serious attempt at becoming a spacefaring civilization. The technologies developed, the international partnerships forged, and the scientific discoveries made will echo through centuries. The moon becomes our testing ground for Mars, our laboratory for deep space operations, and potentially our first extraterrestrial home. As we stand on the threshold of this new era, the questions multiply. How will permanent lunar bases change human society? What discoveries await in the moon's ancient rocks and ice deposits? And perhaps most intriguingly, how will this giant leap transform our species' relationship with the cosmos itself? The engineering challenges of returning to the moon dwarf those faced during Apollo. Where the 1960s program operated with slide rules and primitive computers, Artemis must solve problems of unprecedented complexity while meeting modern safety standards that demand near-perfect reliability. The Space Launch System represents the culmination of 6 decades of rocket engineering evolution. Standing 322 feet tall and weighing 6.2 million pounds when fully fueled, this behemoth generates 8.8 million pounds of thrust at liftoff, 15% more than the mighty Saturn V. Yet raw power tells only part of the story. The SLS core stage, built by Boeing, stretches 212 feet and contains 730,000 gallons of supercooled liquid hydrogen and liquid oxygen. These cryogenic propellants present extraordinary challenges. Liquid hydrogen exists at -423 degrees Fahrenheit, just 37 degrees above absolute zero. At these temperatures, metals become brittle, seals fail, and even the slightest leak can trigger explosive reactions. Managing these propellants requires a revolution in ground systems. The mobile launcher platform weighs 11 million pounds and stands 400 feet tall, essentially a skyscraper, on tracks. Its umbilical systems must simultaneously feed propellants, electrical power, communications and environmental controls to the rocket while being capable of rapid disconnection at launch. The 4 RS-25 engines powering the core stage are themselves masterpieces of engineering. Each engine, originally developed for the Space Shuttle program, generates 438,000 pounds of thrust while operating at pressures exceeding 3,000 pounds per square inch. These engines burn propellant at a rate that would drain an average swimming pool in under 25 seconds. Attached to the core stage are 2 solid rocket boosters, each containing 1.6 million pounds of solid propellant. These boosters, derived from Space Shuttle technology but stretched and enhanced, provide the initial kick needed to escape Earth's gravitational well. The solid propellant mixture burns at temperatures exceeding 5,000 degrees Fahrenheit, hot enough to melt copper. Orion's design philosophy prioritizes crew survival above all else. The spacecraft's heat shield measures 16.5 feet in diameter and consists of avcoat material, a honeycomb structure filled with a resin that ablates during atmospheric re-entry. During return from the Moon, Orion will slam into Earth's atmosphere at 25,000 miles per hour, generating temperatures approaching 5,000 degrees Fahrenheit. The crew module's structure utilizes advanced aluminum-lithium alloy, providing strength-to-weight ratios impossible with conventional materials. Inside, the spacecraft maintains sea-level atmospheric pressure, while protecting occupants from radiation levels 100 times higher than those experienced in low Earth orbit. Environmental control systems aboard Orion must function flawlessly for weeks in the harsh environment of deep space. The spacecraft carries redundant air recycling systems, water recovery technology, and waste management facilities. Every component must operate reliably despite temperature swings from -250 degrees in shadow to +250 degrees in sunlight. Navigation and guidance systems represent another technological marvel. Orion employs a hybrid system, combining traditional inertial navigation with GPS capability and optical navigation using star trackers. During lunar operations, the spacecraft must autonomously maintain precise orbital mechanics while communicating with Earth across distances exceeding 238,000 miles. The European Space Agency contributes the service module, providing propulsion, power, and life support. This module contains 33 engines of various sizes, from the main engine generating 6,000 pounds of thrust to tiny attitude control thrusters. Solar arrays spanning 63 feet generate enough electricity to power 2 average homes. Perhaps most impressive is the integration challenge, ensuring thousands of components from dozens of contractors work together flawlessly. A single failure could doom the crew, making redundancy and reliability paramount concerns. Every system includes backup systems, and many include backup systems for the backup systems. Testing these integrated systems pushes the boundaries of ground-based simulation. NASA's facilities replicate the vacuum of space, solar radiation, thermal cycling, and vibration loads. Computer models process millions of variables simultaneously, predicting system behavior across every conceivable scenario. Orbiting the Moon in a unique halo orbit, the Lunar Gateway represents humanity's first space station beyond Earth orbit, and the critical infrastructure enabling sustainable lunar exploration. This outpost, roughly 1/6 the size of the International Space Station, or Artemis, will serve as staging ground, communications relay, and safe haven for crews traveling between Earth and the lunar surface. The Gateway's orbital mechanics showcase elegant engineering solutions to complex gravitational challenges. Traditional lunar orbits suffer from instability due to gravitational perturbations from Earth and the Sun, requiring frequent course corrections that consume precious fuel. The Gateway instead occupies a near-rectilinear halo orbit, or NRHO, a gravitationally stable pathway that loops around the Moon's north and south poles. This orbit offers remarkable advantages. At its closest approach, the Gateway swings within 1,000 miles of the lunar surface, enabling efficient crew and cargo transfers to surface bases. At its farthest point, it extends 43,000 miles from the Moon, providing unobstructed communications with Earth for 14 of every 17 days. Most importantly, this orbit requires minimal fuel to maintain, conserving resources for mission operations. The Gateway's construction begins with the Power and Propulsion Element, or PPE, built by Maxar Technologies. This foundation module provides solar power generation, electric propulsion, and communications capabilities. 4 massive solar arrays generate 60 kilowatts of electrical power, enough to supply 40 average homes, while ion thrusters provide the gentle but continuous thrust needed for orbital maintenance. Ion propulsion represents a revolutionary technology for deep space operations. Unlike chemical rockets that produce massive thrust for short periods, ion thrusters generate tiny amounts of thrust continuously for months or years. Xenon gas atoms are electrically charged and accelerated to speeds exceeding 67,000 miles per hour. Though the thrust equals the weight of a sheet of paper, the cumulative effect over time enables major orbital changes using minimal propellant. The Habitation and Logistics Outpost, or HALO, provides crew quarters, life support systems, and operational facilities. Built by Northrop Grumman, this module utilizes proven technologies from the Cygnus cargo spacecraft, while incorporating upgrades for the deep space environment. Interior volume equivalent to a small apartment accommodates 4 crew members for up to 30 days. International partnerships define the Gateway's identity as humanity's collaborative outpost. The European Space Agency contributes the International Habitation Module, or IHAB, providing additional crew quarters and research facilities. The Japan Aerospace Exploration Agency, or JAXA, supplies the logistics module for cargo storage and experiment operations. The Canadian Space Agency provides the next-generation robotic arm system for external maintenance and cargo handling. These partnerships extend beyond hardware contributions. Crew assignments include astronauts from multiple nations, sharing operational responsibilities and scientific expertise. This international cooperation mirrors the ISS model while extending humanity's collaborative reach to deep space for the first time. The Gateway's scientific capabilities transform our understanding of lunar and deep space environments. Advanced telescopes operating beyond Earth's atmospheric interference and radio frequency pollution observe the universe with unprecedented clarity. The far side of the Moon, permanently shielded from Earth's radio emissions, provides the quietest electromagnetic environment in the inner solar system. Biological experiments aboard the Gateway investigate the effects of deep space radiation and reduced gravity on living organisms. Understanding these impacts proves crucial for eventual Mars missions, where crews will experience similar conditions for years. Plant growth experiments may identify food production methods for future lunar bases and Mars colonies. Communications. Relay capabilities enable continuous contact with lunar surface operations. When Earth disappears behind the Moon during the 14-day lunar night, surface crews rely on the Gateway to maintain communication with mission control. High-gain antennas provide data relay rates exceeding 100 megabits per second, supporting real-time video conferences and scientific data transmission. The Gateway also serves as an emergency shelter for lunar surface crews. Should a critical system failure occur at a surface base, crews can evacuate to the gateway within hours rather than waiting days for Earth-based rescue missions. Medical. Facilities aboard the station provide advanced life support capabilities unavailable on the lunar surface. Cargo operations through the gateway enable the delivery of massive payloads to the lunar surface. Commercial cargo vehicles dock with the station, transferring supplies and equipment for relay to surface bases. This hub-and-spoke model dramatically reduces the cost and complexity of lunar surface operations while enabling rapid response to changing mission requirements. The lunar South Pole represents one of the most scientifically valuable and operationally challenging destinations in the solar system. Here, in permanently shadowed regions that have remained dark for billions of years, humanity may find the keys to sustainable space exploration and unlock secrets about the early history of Earth and the Moon. These permanently shadowed regions, or PSRs, exist due to the Moon's minimal axial tilt of only 1.5 degrees. Unlike Earth, where seasonal variations ensure sunlight reaches all locations throughout the year, certain lunar craters near the poles remain in perpetual darkness. Some regions haven't seen sunlight for over 2 billion years, making them among the coldest places in the solar system, at temperatures reaching -397 degrees Fahrenheit. Within these frozen wastelands lies treasure beyond measure. Water ice deposits estimated to contain billions of tons of frozen water. The Lunar Crater Observation and Sensing Satellite, or LCROSS mission in 2009, confirmed these deposits by deliberately crashing into Cabeus crater and analyzing the resulting debris plume. Spectroscopic analysis revealed not only water but also hydrogen sulfide, ammonia, methane, and carbon dioxide, a frozen record of volatile compounds delivered by comets and asteroids over geological time. Water ice represents the ultimate space resource multiplier. Through electrolysis, water splits into hydrogen and oxygen, the same propellants powering the space shuttle's main engines. A single ton of water ice can produce enough rocket fuel to return a crew from the lunar surface to Earth. This transforms the Moon from a destination requiring massive Earth-based supply lines into a refueling station for deep space exploration. The extraction and processing of lunar water ice presents unprecedented engineering challenges. Excavation equipment must operate in temperatures that would shatter conventional machinery, in vacuum conditions, where heat dissipation occurs only through radiation, and in locations where Earth communication is limited or impossible. Solar. Power systems effective elsewhere on the Moon become useless in permanent shadow. Nuclear power systems offer the only viable energy source for PSR operations. NASA's kilopower reactor, currently under development, would provide 10 kilowatts of continuous electrical power, enough to support a small research station. These compact reactors utilize uranium fuel and Stirling engine conversion systems, operating reliably for years without maintenance. Mining operations in permanently shadowed regions require revolutionary robotics. Autonomous excavators must navigate terrain never mapped in detail, identify ice-rich deposits through subsurface sensing, and extract material while operating in communication blackouts lasting hours. These machines must repair themselves, adapt to changing conditions, and continue operations despite equipment failures that would cripple terrestrial mining operations. The scientific opportunities at the South Pole extend far beyond resource extraction. The permanently shadowed regions preserve a 4.6 billion-year record of volatile delivery to the inner solar system. Analyzing ice composition reveals the chemical signatures of ancient comets and asteroids, providing insights into conditions during the solar system's formation. Samples from different depths within ice deposits chronicle the varying bombardment. History of the inner solar system. Periods of intense comet activity correlate with mass extinction events on Earth, suggesting these lunar archives may help predict future impact threats to our planet. Some ice deposits may contain organic compounds, the carbon-based molecules essential for life. Landing at the South Pole demands navigation precision impossible during Apollo missions. Targeted landing sites occupy areas just miles across, requiring guidance accuracy within hundreds of feet rather than the miles-wide zones acceptable for Apollo. Hazard avoidance systems must identify safe landing spots among boulder fields and crater rims in real time during powered descent. The Artemis 3 human landing system faces the additional challenge of landing a 100-ton Starship vehicle on terrain that may not support such massive loads. Ground-penetrating radar must assess soil-bearing strength during approach, while multiple engines provide redundancy against failures that could doom the mission. Surface operations at the South Pole occur in a surreal environment where Earth hangs motionless in the black sky, never rising or setting due to the moon's synchronous rotation. Navigation relies on star positions and inertial guidance systems rather than familiar landmarks. Crews work in perpetual twilight, with only earthshine and artificial lighting illuminating the alien landscape. Temperature variations present constant challenges. Equipment functioning normally in sunlit areas may fail catastrophically when moved into shadowed regions. Spacesuits require advanced thermal management systems to protect crew members during transitions between temperature extremes that exceed 500 degrees Fahrenheit. The communication challenges of South Pole operations necessitate relay systems for continuous Earth contact. The Gateway provides primary communications relay, while surface relay stations extend coverage into shadowed regions where direct Earth communication is impossible. The transformation of temporary lunar outposts into permanent human settlements represents one of the greatest engineering challenges in human history. Building a sustainable lunar city requires mastering construction techniques, life support, systems and resource utilization technologies that have never been attempted on such scales beyond Earth. Lunar habitat construction begins with fundamental material science challenges. The Moon's lack of atmosphere eliminates traditional construction techniques requiring air-based curing or chemical processes. Temperature extremes ranging from -250 degrees Fahrenheit to +250 degrees Fahrenheit stress materials beyond terrestrial design limits. Meteorite impacts, impossible on Earth due to atmospheric protection, pose constant threats to structural integrity. In situ resource utilization, or ISRU, provides the foundation for large-scale lunar construction. Rather than shipping, building materials from Earth at costs exceeding $10,000 per pound, lunar settlements must manufacture construction materials from local resources. Lunar regolith, the fine-grained surface material, contains silicon, aluminum, iron, and other metals essential for construction. The lunar concrete manufacturing process begins with regolith processing through magnetic separation to extract iron particles, followed by chemical processing to isolate aluminum and silicon compounds. Solar concentrators focus sunlight to achieve temperatures exceeding 3,000 degrees Fahrenheit, melting regolith into glass-like materials suitable for construction blocks. These lunar bricks provide radiation shielding equivalent to several feet of Earth-based concrete. Three-dimensional printing revolutionizes lunar construction by enabling complex structures without traditional construction crews. Massive robotic printers, potentially delivered during cargo missions, extrude melted regolith layer by layer to create habitat shells, landing pads, and infrastructure components. These automated systems operate continuously during the 14-day lunar day, taking advantage of abundant solar power for energy-intensive melting operations. Underground construction offers superior protection against radiation, meteorites, and temperature extremes. Lunar lava tubes, discovered through radar imaging, provide ready-made underground spaces large enough to accommodate entire cities. These natural formations, created by ancient volcanic activity, offer stable environments protected from the harsh lunar surface conditions. Expanding lava tube habitats requires excavation and sealing techniques adapted for lunar conditions. Robotic mining equipment removes loose material while preventing structural collapse. Inflatable habitat modules, launched from Earth and deployed within lava tubes, provide immediate pressurized living spaces while permanent construction proceeds around them. Life support systems for permanent lunar settlements must achieve near-perfect recycling efficiency. The ISS currently recycles approximately 93% of water and oxygen, but lunar settlements require efficiency approaching 99% to minimize Earth-based resupply requirements. Advanced atmospheric processing systems remove carbon dioxide, trace contaminants, and maintain optimal oxygen levels for human health. Water recycling systems must process not only human waste, but also industrial wastewater from manufacturing. Operations, scientific experiments, and equipment maintenance, multi-stage filtration, reverse osmosis, and chemical processing ensure water purity while recovering valuable dissolved minerals for agricultural and industrial applications. Food. Production systems utilize controlled environment agriculture, adapted for lunar gravity and artificial lighting. Hydroponic and aeroponic systems eliminate the need for soil while maximizing crop yields per unit area. LED lighting systems provide optimized spectral output for plant growth while minimizing electrical power consumption. Crop selection focuses on species providing maximum nutritional value, growing efficiently under artificial conditions, and offering psychological benefits through familiar foods. Potatoes, soybeans, wheat, and various vegetables provide balanced nutrition while supporting food security independent of Earth-based supplies. Advanced genetic modifications may enhance crop performance under lunar conditions. Manufacturing capabilities enable lunar settlements to produce tools, equipment, and consumer goods locally, rather than relying entirely on Earth-based supplies. Metal processing facilities smelt lunar ores into aluminum, iron, and titanium for construction and manufacturing. Electronics manufacturing, utilizing silicon extracted from regolith, produces solar panels, computer components, and communication equipment. The lunar settlement economy develops around resource extraction, manufacturing, and services supporting both lunar residents and Earth-based activities. Lunar manufactured solar panels, constructed from local materials but assembled with precision impossible on Earth due to atmospheric interference, may prove superior to terrestrial equivalents. Unique manufacturing processes enabled by vacuum, conditions, and low gravity create materials and products impossible to produce on Earth. Transportation infrastructure connects multiple lunar settlements through pressurized rovers, landing pad networks, and potentially magnetic levitation systems, utilizing superconducting materials that function efficiently in lunar vacuum conditions. Communication networks provide high-speed data transmission between settlements and Earth, supporting educational, entertainment, and commercial activities. Research facilities within lunar settlements advance scientific understanding while developing technologies applicable to Mars exploration and asteroid mining. Low gravity and vacuum conditions enable experiments impossible on Earth, potentially leading to breakthrough discoveries in materials, science, biology, and physics. The Moon represents far more than humanity's second home. It serves as the essential stepping stone, enabling exploration and settlement throughout the solar system. The infrastructure, technologies, and operational experience gained through lunar settlement provide the foundation for reaching Mars, mining asteroids, and establishing humanity as a truly spacefaring civilization. Mars mission planning reveals why lunar experience proves indispensable. The journey to Mars requires 9 months of travel time, compared to 3 days for lunar missions. Crews must survive in deep space radiation environments for over 2 years, total mission duration, facing equipment failures, medical emergencies, and psychological challenges without possibility of Earth-based rescue. The technologies and operational procedures developed through lunar settlement provide the essential experience base for managing these unprecedented challenges. Propellant. Production represents the most crucial technology transfer from lunar to Mars operations. The same electrolysis systems that split lunar water ice into hydrogen and oxygen propellants work equally well processing Martian water ice and atmospheric carbon dioxide. However, the scale and complexity of Mars propellant production far exceed lunar operations, requiring industrial facilities capable of producing hundreds of tons of fuel for return journeys. Lunar manufacturing capabilities directly enable Mars mission hardware production. The massive spacecraft required for Mars missions, potentially exceeding 1,000 tons fully fueled, prove economically prohibitive to launch from Earth's deep gravitational well. Manufacturing these vehicles at lunar industrial facilities, utilizing materials extracted from lunar resources, reduces Mars mission costs by orders of magnitude while enabling much larger and more capable spacecraft. In-space assembly techniques, perfected through lunar operations, become essential for Mars mission vehicles. These spacecraft, too large for single launch delivery, require construction from multiple components delivered separately and assembled in space. Lunar industrial facilities provide the controlled environment, skilled workforce, and specialized equipment necessary for complex spacecraft assembly operations. Life support system reliability, critical for Mars missions, receives thorough testing through years of lunar settlement operations. The closed-loop environmental systems required for Mars missions must function flawlessly for years without Earth-based resupply or maintenance support. Lunar settlements provide the testing ground for these systems under realistic deep space conditions while maintaining the safety net of Earth-based rescue if catastrophic failures occur. Medical capabilities. Developed for lunar settlements, directly apply to Mars missions and beyond. Surgical procedures, emergency medicine, and long-term health monitoring systems tested on the Moon prepare medical personnel for the challenges of providing comprehensive healthcare months away from Earth. Pharmaceutical manufacturing from local resources, essential for lunar settlements, becomes even more critical for Mars missions where Earth-based medication resupply is impossible. Asteroid mining, enabled by lunar infrastructure, opens access to resources that dwarf terrestrial supplies. A single metallic asteroid contains more platinum than has ever been mined on Earth, more rare Earth elements than exist in known terrestrial deposits, and enough iron to supply human civilization for millennia. However, accessing these resources requires spacecraft, equipment, and operational capabilities far beyond current Earth-based launch systems. Lunar mass drivers, electromagnetic launch systems utilizing the Moon's low gravity and lack of atmosphere, can accelerate mining equipment and supplies to asteroid intercept trajectories using only electrical power. These systems, impossible to operate from Earth due to atmospheric drag, enable economical delivery of massive mining equipment to near-Earth asteroids. The economic implications of space-based resource extraction transform human civilization. Platinum group metals, essential for electronics and catalytic processes but extraordinarily rare on Earth, become abundant through asteroid mining. Water ice, extracted from asteroids and delivered to Earth orbit, provides propellant for spacecraft and industrial processes while potentially supporting orbital manufacturing facilities. Solar power satellite construction, utilizing lunar and asteroid resources, addresses Earth's growing energy demands while eliminating atmospheric pollution. These massive structures, assembled in space using extraterrestrial materials, beam clean energy to Earth through microwave transmission. The Moon provides the industrial base for manufacturing solar panel components, structural materials, and assembly facilities. Interstellar probe missions benefit enormously from lunar and asteroid infrastructure. Spacecraft destined for other star systems require velocities exceeding conventional chemical propulsion capabilities. Solar sails, ion drives, and fusion, ramjets manufactured in space using asteroid resources, enable probe velocities approaching significant fractions of light speed. Lunar observatories, freed from atmospheric interference, track these probes across interstellar distances while maintaining communication through advanced beam systems. The expansion of human civilization beyond Earth transforms our species. Long-term survival prospects. Catastrophic events that could devastate Earth-based civilization, asteroid impacts, supervolcanic eruptions, or nuclear conflicts, cannot threaten settlements distributed across multiple worlds. This redundancy ensures human civilization's continuity regardless of terrestrial disasters. Educational and cultural exchange between Earth and space settlements creates unprecedented opportunities for human development. Children growing up in lunar gravity develop unique physical and cognitive capabilities, while Earth-based education systems incorporate space-based research and manufacturing into curricula. Art, literature, and music created in space environments reflect experiences impossible on Earth, enriching human culture. The Artemis program represents the first step in humanity's greatest adventure, the expansion of our species throughout the solar system and beyond. The technologies demonstrated, infrastructure established, and operational experience gained through lunar settlement provide the essential foundation for this cosmic journey. What begins as a return to the Moon evolves into humanity's transformation, from a single planet species into citizens of the galaxy. As we stand on the threshold of this new era, the Moon calls to us once again. This time, we answer not for national prestige or scientific achievement alone, but for the future of human civilization itself.